Welcome back. So today we're going to be talking about turbulence modeling, which is one of the most important areas of high-performance computing and computational science. So when we want to design a new aircraft or an automobile or a turbine engine, the blades for a turbine, generally speaking, we're going to need to simulate some fluid flow equations to estimate quantities of interest, like the lift and drag on the wings and the body of an aircraft, for example. Now, we, in general, might want to solve the full Navier Stokes equations with a direct numerical simulation, which would resolve all of the scales in space and time. So here I'm going to show you one of my favorite movies of a direct numerical simulation. But it is typically very difficult to simulate these fluid flow equations over the entire aircraft or over an entire automobile. So instead, what researchers often do is zoom into a particular piece, like this section of an airfoil, and solving the full flow field equations for this section of the airfoil is still exceedingly expensive. Okay, so this is a supercomputer computation. I believe it'll show here in a little bit how many hours. So this is the grid that's being generated. And a preliminary Reynolds average Navier Stokes solution is used to extract values for the boundary conditions. This is 35 million core hours. Okay, so extremely expensive just to get one section of an airfoil, let alone the full aircraft. Okay. And so typically it is too expensive to run direct numerical simulations or simulate all of the scales of the Navier Stokes equations all at once for something like an aircraft or a ship. Okay? And so even with Moore's law of exponentially growing computer power, it will still take, at this current rate, 100 or more years to be able to simulate the largest scale turbulent problems at all resolutions in space and time. And that's just for one run of this simulation. Now, when you want to do design optimization, inverse optimization, for example, to design the shape of a wing, you're having to run many of these simulations in an iterative loop. And so it'll be even harder to use this for design, optimization, and real-time control. And so that's where turbulence modeling comes in. Instead of simulating all of the scales of the Navier Stokes equations in space and time, we're going to make approximations that allow us to get engineering quantities of interest much more efficiently. Okay, so that's what I'm going to talk about today. And this is going to lead in very naturally to modern methods in machine learning and deep learning, which is really stands to revolutionize turbulence modeling. Okay, so I'm going to jump in, and some of this is going to be a review from the last few weeks' lectures. So the Reynolds averaging approach to the Navier Stokes equations, and we're going to kind of zoom into one turbulent example here, is to take the Navier Stokes equations, in this case the incompressible Navier Stokes equations, so the momentum equation and the mass continuity equation. And what we're going to do is look at the averaged velocity field. So this is an unsteady, time-varying velocity field, just like that movie I showed you. But we're going to average in time, and we're going to try to model these time-averaged quantities. So Reynolds, Osborne-Reynolds, the same Reynolds as the Reynolds number, proposed this decomposition of this separation of your velocity field u, which is a function of space and time, into a time averaged component, u bar, and the fluctuating components, u prime. And so u bar is just a time average, and u prime is everything else that's not in that time average. And the idea is we're going to take this decomposition, plug it into the Navier Stokes equations, and average those equations to try to get a simplified equation of just this mean flow variable u bar. And what we hope is that we get a simpler set of equations to solve that is less expensive, but gives us large-scale information about our engineering system, like the average drag or the average lift, or whether or not my airfoil, the flow over my airfoil is going to separate or not. Okay? And so when you plug this Reynolds decomposition into, for example, the mass continuity equation, now this is a review, I'm just going to walk you through really briefly, you essentially get 6 terms because this is the divergence of u, so partial u partial x plus partial v partial y plus partial w partial z or z, both in the mean and the fluctuating components. And so there's a lot of tricks we can play, and I've shown you this before. If I take and I time average this entire equation, so every term here, well, the time average of a time average is just itself, so these three terms remain unchanged. But the time average of my fluctuating derivatives goes to 0, because those, by definition, when I averaged them, they were 0. They were everything that was not in the mean flow. So when I average, I kill those three terms, which implies that my mean flow divergence is equal to 0. Now, by a similar argument, if these three terms are equal to 0, then it stands to reason that these three terms before I time average were also equal to 0. And so it means that the divergence of my fluctuating components are equal to 0. So this is the kind of game you can play when you do this Reynolds average Navier Stokes, so this Reynolds decomposition. So I take my, my decomposition, I plug it into my continuity equation, and I find these two equations that the divergence of my mean flow and my fluctuating velocity field are both equal to 0. Okay? Now, when we do the same thing for the momentum equation, it's a little bit more complicated. So I'll just briefly walk through here, and this is going to set up the turbulence closure problem that we're going to look at in the next half of the video. So this is just the x component of the momentum equation. So this is, in general, 3 equations for u, v, and w. So I'm just looking at the first equation for the x momentum. And when I take my Reynolds decomposition and I plug it into my Navier Stokes equations, what we find is kind of this pretty nasty expression here. This is what I get when I just plug this into my momentum equation. And we're going to do the same thing as before. We're going to time average everything. But before we do that, we're going to notice that this term here, this u bar t, that is always 0 because this term is always 0 because u bar is not time varying. So this term is going to go away. And then when we time average everything, a lot of terms drop out. And I went through this kind of in another lecture, so if you want the details, you can find it. But basically, all of the fluctuating components and all of the terms with one fluctuating component are going to drop out. And so all that's left are these average quantities and these quantities that have 2 fluctuating components in their averages. And so you can kind of collect all of these terms like this, so massively simplified equation. But remember, we wanted to find an equation that was simpler, that was just in terms of this mean flow u bar, because those give us kind of the big average quantities we might care about for design optimization. But this equation is not just a function of my mean flow variables. It also has these turbulent fluctuations u prime x and v prime u prime y, things like that, which vary in time and space. So I need to know what's happening in the full turbulent flow field to solve for these average quantities I care about. And so in general, understanding and modeling these terms here is going to be central to the closure modeling problem. I'm going to simplify just one step further. So you can use this identity here, which is basically just the chain rule of these middle terms would give you the left terms plus the right terms. I've written it this way because these are the terms that we have on the left here. And notice that every term in this right column, if I added those up, it would be the same as little u prime times the divergence of vector u prime. And remember that our divergence of our fluctuating components is 0. So these 3 terms die out. And so I can replace these 3 sums, the sum of these 3 terms with these terms here. And so I'm going to replace it like this, and I'm writing all of my partials out explicitly instead of with subscripts. And this is the u component, the x component of my Reynolds averaged Navier Stokes equations. Okay, good. So I'm just going through and kind of showing you this is all rigorously derived from the equations of motion. People have been doing this for 100 years, okay? And these terms here are called the Reynolds stresses. And in particular, I mean the u prime bar and u prime v prime bar. Those are the Reynolds stresses because when I take their spatial gradient, they have units of force per volume, just like these stresses down here, the pressure and the viscous diffusion forces. And so these can be kind of thought of as generalizations of these pressure forces and diffusion forces, but due to these turbulent fluctuations. They're creating a stress on the mean flow that we want to model. Good, and the whole closure problem is trying to approximate these mean flow quantities without considering these turbulent fluctuations. So what we want to do is essentially find a model for these Reynolds stresses in terms of the mean flow. That's the whole name of the game, and that's what at least Reynolds average Navier Stokes closure modeling is all about. Good, so here are our Reynolds stresses. Again, the x component of the momentum equation. You can do some other things I want to just show you. We're going to go into different closure models in a minute, but there's a couple of concepts that I want to show you that are really, really important. So you can take your Reynolds stresses, and we're going to try to build a model for these Reynolds stresses now. So what I can do is I can take my Reynolds average Navier Stokes equations. I take my Reynolds decomposition, plug it into the Navier Stokes equations. And now, instead of just averaging, I'm going to multiply by my fluctuating component, u prime, and then average. And you get something pretty ugly here, okay? So I'm not going to walk you through this. You can derive this yourself, or even better, go download Lex Smith's notes from Princeton MAE 553, and you can walk through exactly how this works. But so again, a lot of these terms are going to simplify, and notice that you get for these u prime Reynolds stress terms, now I have terms that include 3 fluctuating components, u prime, and u prime sub x. And so what this means is that when I want to build a model for these Reynolds stresses, which are the second moments of my turbulent fluctuations, I'm going to need to include these third order moments, or triple correlations of my turbulent fluctuations. And this never ends. If I took this equation and I multiplied it by u prime and I time average, I could get an equation for these kind of triple stresses. But those triple stresses would have 4th order correlations that they depend on. And the 4th order correlations would have 5th order correlations. And this never ends. This is fundamentally a mathematical closure problem. And it's kind of related to lots of other closure problems we've seen, like the Koopman operator and things like that. Okay, so I just wanted to show you it's not that easy to just build a simple model for these Reynolds stresses. This kind of just gets worse and worse the more you try to close the problem. There is an alternative approach, which I'm going to walk through, which is essentially, here, I'm going to write this here. So going back to our x momentum equation, you can write this in kind of Einstein notation like this. So this is actually all 3 of the equations. So if I equals 1, that would be the x equation. If I equals 2, that would be the y equation. And if I equals 3, that would be the z or z equation. And so you can write the whole kind of Reynolds average Navier Stokes problem like this, where I've pulled my partial derivative out, and all of these terms are my stresses. Okay, I've got my pressure, my viscous diffusion, and my Reynolds stresses here. Okay, good. And so one of the things that people use the most often to model these systems is called the turbulent kinetic energy. So what you want to do is try to understand, you have all of those turbulent fluctuations. How are those being driven by the mean flow, and how does the mean flow get driven by those turbulent fluctuations? So there's this constant trade-off of energy between the mean flow kinetic energy and the turbulent kinetic energy. And turbulence closure models are essentially going to try to model those Reynolds stresses by modeling how this energy flow occurs only using mean flow variables. So we define the turbulent kinetic energy here, K, and this is going to be the K from K epsilon models and K omega models that you've probably heard of in the past. And with a little bit of math, you can essentially derive this turbulent kinetic energy equation. Again, this is done really nicely in Lex Smith's course notes, but this is what you get when you essentially derive the equation for the time variation of K. And I'm going to walk you through what each of these terms means. Okay, so this is the rate of change of my turbulent kinetic energy in time, and it's driven by these terms on the right. So we have convection by the mean flow, Essentially, K is being convected by these large mean flow currents. I have pressure diffusion. I'm not going to talk about what all of these terms mean. I have something called turbulent transport, which again involves this triple moment here, this kind of U prime, U prime, U prime. And again, subscript here, UI1 would be U, U sub 2 would be V, U sub 3 would be W, and partial XI, that means partial X, partial Y, partial Z, okay? The del squared K del X squared is just, normal viscous transport. This is the term I really want to talk about, this turbulence production term, which is my Reynolds stresses times the gradient of my mean flow. I'll talk about this in a minute. And then I have dissipation terms, basically turbulence just dissipating into heat, okay? And so there's this really nice figure that I saw in Lex's notes, but he pulled it from Bradshaw's 1971 book, which basically shows, all of these different terms are kind of competing to grow or to shrink the turbulent kinetic energy and to trade energy from the mean flow into energy into the turbulent scales and vice versa. So that's what we're going to be modeling. And I'll point out this turbulence production is one of, I think, the most important for me conceptually, because it says essentially that our turbulence kinetic energy increases when we have a large shear in the mean flow. So if I have an average flow, like a shear layer, where I have really, really fast flow and slow flow, there's a large shear between those two flows. That's going to drive the development of lots of turbulence. It's going to pump energy into the turbulent scales from this big mean flow. And so for me, this has been very useful conceptually to understand what types of features in a turbulent flow drive the small scale turbulence. So anytime the flow separates over your wing and creates a shear layer, you know it's going to be driving lots of turbulent energy production. Okay, good. So back to the Reynolds averaging problem and back to our closure problem. So we want to model the Reynolds stresses as a function of the mean flow. If we can do that, then we can solve this efficiently, and we can get mean flow quantities like the average lift, the average drag, things like that, okay? And the simplest approach, kind of the approach actually that people still take today, this is an old approach, is called Eddy viscosity modeling. So basically what you're going to do is you're going to say that all of those tiny little turbulent scales that generate those Reynolds stresses, they basically act like viscosity in the Navier Stokes equations. They basically act like this diffusion term here. And so we want to find kind of the effective viscosity of the turbulence. And so this was actually proposed a long time ago by Boussinesq in 1877, is that we can model these turbulent fluctuations as some eddy viscosity, some effective viscosity nu sub t, times this kind of, gradients of the mean flow. So partial u partial y plus partial v partial x for a 2D flow, like this channel flow up here, okay? And this gets a little more complicated in 3D. You can essentially, in 3 dimensions, write each of these components here. And I picked up this little term, which is 2/3 the kinetic energy times the Dirac delta function, in case I want to look at the stress U1 bar, or U2 bar, or U3 bar. I'll need to consider this term here. But the big idea is that we are modeling all of those turbulent scales in terms of this effective viscosity, this Eddy viscosity model, nu times mean flow quantities. And by far the simplest model is just say nu t is a constant. So you could totally just pick a constant, tune this empirically for a pipe flow or a channel flow or a shear flow, and plug that constant in, and it will do, all right. It's not a great model. It's a pretty bad model. Prandtl made a really important correction to this Eddy viscosity model, which essentially says that this effective viscosity changes in space depending on the mean flow shear. Okay, so he was considering boundary layers where the boundary layer thickness grows and where the turbulence evolves both in space and away from the boundary, from the wall. And so Prandtl proposed this kind of mixing length hypothesis that essentially this effective viscosity is a function of this mixing length squared times the shear in the y direction. So this kind of gradient of u in the y direction. And so if you plug this in for our eddy viscosity, you get a better model for these wall-bounded flows, okay, for boundary layer flows. This is our mixing length. And you can kind of tune that empirically or make arguments for what that mixing length is. Again, that's like a whole thing you would do. And then there are a whole family of more sophisticated models that try to model this turbulent kinetic energy more effectively. Okay, so those kind of eddy viscosity models, the simple, constant, and Prandtl models are very, very simple. That's like before computers. This is what you would do now that we have computers, are these 2 PDE or 2 equation turbulence models like K epsilon or K omega. And here K, again, is the turbulent kinetic energy. It's that equation I derived for you. And epsilon is the rate of dissipation of the turbulent kinetic energy. So in that big TKE equation I showed you before, you could basically lump all of the terms that go to dissipate K, and you call those epsilon. And then you write a new differential equation for epsilon, what causes it to grow and shrink. And you can essentially solve these 2 PDEs with your RANS equations, and you get a better, more accurate prediction of your turbulent mean field. And this would be the eddy viscosity nu as a function of K and epsilon, the density of the fluid rho, and this constant C mu. Now, C mu has been empirically determined to be about 0.09, but this is the formula. Now, again, K epsilon models, like if you run any commercial turbulence software, there's an option, for what turbulence model you want to select or to use, and K epsilon is one of the standard models. But it's been known for a long time that this is not a good model when you have adverse pressure gradients or reverse flow. So for example, if I have flow over a wing and my wing's at a high angle of attack, or it's a droop wing, or there's a gust, I'm going to get this separated flow structure that's going to cause vortex shedding. And if I look at my average flow, my mean flow, it's going to look like a separation bubble. It's going to look like the flow separates and reattaches at some point. And if I look at my boundary layer profile, upstream, it's a normal boundary layer profile. But right in that separation bubble, you see that the flow reverses before it catches up to the free stream. So this is a recirculation bubble or a region of reverse flow. This is called an adverse pressure gradient that's causing the flow to reverse. Now, these K epsilon models are notoriously bad for these kinds of separated flows. But this is a really important problem that people actually care about in aircraft design, is predicting when my flow is going to separate, when my wing is going to stall. That's a critical thing to predict. And so these are just not that great of models for that. Okay, so another really, really useful model in the literature is the Spalart-Almaraz model, which is a 1 equation model, so more efficient than K epsilon. And it's actually been tailored for aerospace applications. I'm sorry, autocorrect killed one of the L's here. This is 2 L's Almaraz here. This is one of the most cited papers in AIAA history. So over 10,000 times this has been cited because it's so useful, and it has very nice physical derivations of the tuning constants of this model. And again, it's been specifically tailored for aerospace applications, like predicting the lift and drag on wings and on aircraft. So you can use this model for designing your aircraft. You can change or tweak the geometry of your wing and fairly rapidly figure out what these average quantities are going to be, and then re-optimize and redesign based on these predictions. So this one's really, really useful, cornerstone of aerospace engineering. Okay, good. So that was turbulence closure modeling using the Reynolds average Navier Stokes equations. Now for the rest of this, I'm going to tell you about a whole different perspective called large eddy simulation, or LES. And these are really kind of the 2 big families of turbulence closure modeling. You have your Reynolds average Navier Stokes and your large eddy simulations. And LES was proposed more recently. So you remember Boussinesq was 1877. Large eddy simulation was proposed much more recently in the computational era by Smagorinsky in 1963. And Smagorinsky, I believe, was the director of the GFDL lab at Princeton, the Geophysical Fluid Dynamics lab. And so their concern was trying to simulate and predict these large Earth-scale geophysical flows, like the atmosphere, how a hurricane forms. And so again, too complicated to simulate all scales. Smagorinsky proposed that instead of solving the Navier Stokes equations on a very, very high resolution grid, we would solve it on a much lower resolution grid, and essentially low pass filter or coarse grain the Navier Stokes equations. So instead of, this would be far too expensive even for our biggest supercomputers to solve all of the scales of an Earth scale flow. So what we're going to do is coarsen the grid and filter the Navier Stokes equations onto that coarse grid and solve those equations. And when I say, a coarse grid, I mean, maybe you take the surface of the Earth and you chop it up into boxes 100 square kilometers, or maybe 100 kilometers by 100 kilometers. That would be a coarse model. And every 10 or 20 years, we're able to refine that model down and get finer and finer resolution because again, Moore's law and our supercomputers are getting bigger and bigger. But it's still going to be a long time before we can actually resolve all of the scales that matter. So we low-pass filter our Navier Stokes equations onto the coarse grid. And this has its own closure problem, which is essentially the nonlinearity in the flow. And I'm not going to derive this kind of filtering. It's pretty mathematically involved. But the nonlinearity effectively couples your spatial scales. So your big structures depend through nonlinear terms on your little scales, and your little scales depend through the nonlinear term on your big scales, through that convection term in your Navier Stokes equations. And so we need to model what's happening under the hood in each of these little coarse boxes. Each of these little coarse grid boxes has real turbulent fluid variations happening. And so we need a model for the subgrid scale. These are called SGS or subgrid scale models. And in principle, we do the exact same thing for LES, or we have kind of the same tool set for LES that we did for RANS. We're going to use Eddy viscosity modeling and things like that. We're going to make hypotheses about what's happening behind the scenes or underneath this coarse grid, in the full resolution field. And we're going to make approximations about how that's approximately acting like an effective viscosity. And this goes back to this picture of the Kolmogorov energy cascade, where you essentially have, all of these different orders of magnitude scale separation from the biggest vortex to the tiniest vortex. In fact, the Reynolds number is a ratio of the size of the largest vortex in the flow to the tiniest vortex. So this gets bigger for higher Reynolds number flows. And you have all of these different kind of regions where energy transfers from big scales to small scales and medium scales and so on. There's energy transfer. So the production range, again, I said that turbulent fluctuations are produced from shears in the bulk flow, in the mean flow. That happens here. These large structures are pumping energy into the turbulence. And then you have these turbulent vortices splitting and splitting and splitting. This is the inertial range. And finally, you have a dissipation range where the turbulence acts effectively like a viscosity, or at least that's the model. And so the idea here is to basically just chop this off at some point, don't resolve these higher frequencies, these smaller structures, and just treat them as an effective viscosity, just like we did in the RANS equations. Okay, good. Now, why would we do LES over RANS? So here's a video I really like from Think Fluid Dynamics that shows an LES simulation on the top and an unsteady RANS simulation on the bottom for flow past these words. And you can see right off the bat that the LES gives you way more detail into the flow structures. It's much more accurate, especially for shear structures and for the separated region of the flow in the wake. So LES is typically much, much more accurate, but it is obscenely expensive. It is essentially also leveraging supercomputing resources. And so you're using these huge supercomputers to run these LES simulations. If you have the resources and you really want to know about separated structures and unsteady dynamics, this is probably the way to go if you can't do full DNS. So another LES movie I love, this is a team from Johns Hopkins University, Stevens, Game, and Mennevo. And I pulled this from the Physics of Fluids group at University of Twente. They're using LES to simulate the flow past an entire wind farm. Again, there's no way we could do direct numerical simulations at this scale, for these 100-meter wings or 50-meter wings across an entire field, right? Kilometers long. There's no way you could do full simulation of Navier Stokes. So they're going to do large eddy simulations to understand how these wakes interact and how the fluid kind of vorticity interacts in this flow. And I absolutely love this video, so I'm just going to let it play for a little while. And I encourage you to download this for yourself. So, this team is doing great things with LES for renewable energy and lots of other applications. But you're going to see it's going to zoom in a minute, and we're going to, again, kind of see all of the turbulent fluctuations in this flow. Now, is this perfectly accurate? Absolutely not. This is not a full simulation of the Navier Stokes equations. This is not resolving all scales in space and time. Is it useful for engineering to see how mixing occurs and how the wakes impact downstream turbines? Absolutely. You can use this for design and optimization and control. I love this image where they show kind of, you can imagine a smoke line released at a given point in time and how that smoke would mix downstream through the flow. And so this, again, just wouldn't be possible without turbulence closure modeling. This kind of full-scale simulation wouldn't be possible if we tried to simulate the full Navier Stokes equations directly. Okay? All right, so one last kind of parting thought here. I pulled this figure from this website, CFD with a Mission, and they pulled this from a set of slides by Spalart. So remember Spalart from the Spalart-Almaraz model at Boeing. This is a great picture, which essentially shows this detached eddy simulation model, or DES, which was proposed, I want to say, in the 70s. That might not be right, maybe later. But essentially, this detached eddy simulation is built to kind of mix the best of RANS and the best of LES to be more efficient and more accurate. So when the flow is pretty steady and pretty kind of, there's not a lot of adverse pressure gradient or separation, you're going to use RANS. And when the flow is massively separated like this wake down here, you're going to switch to an LES model. And again, lots of math, lots of closure modeling to kind of match these and combine these, but this is a very cool and useful simulation technique as well. Okay, great. So we've talked a lot about turbulence closure modeling and essentially modeling subgrid scales and turbulent fluctuations in terms of larger quantities of interest. And so in the next lecture, I'm going to talk about how we're using deep learning and deep neural networks to start to solve and help with these RANS and LES closure models to make them more accurate and to tailor them with actual high fidelity data. All right, thank you.